Okay, so we'll start this video with a little overview. Remember, we talked about cardiac conduction and how we're going to move those action potentials through the tissues. We're going to start in the SA or the sinoatrial node. Remember that these are spontaneous depolarizations that are occurring. We're going to fire about once every 0.8 seconds or roughly 75 action potentials per minute. From that SA node, those action potentials are going to diffuse, move through the gap junctions across both atria simultaneously. So in the right atrium, it's going to move from that SA node down towards the ventricles, also across and around to come down toward the ventricles or towards the AV valve. At the same time, that action potential is going to conduct across and do the same sort of thing in the left atrium, so that both atria are going to fire simultaneously and contract after that action potential. From the SA node, we're going to move into the AV node, or the atrioventricular node, still located in the atrium, just superior to the right atrioventricular valve. The action potential will transfer into the bundle of His and then into the bundle branch fibers. Those bundle branch fibers are going to run, those bundles are going to run towards the apex of the heart, down the interventricular septum, and then we'll branch into those fast conduction Purkinje fibers to run through the remainder of the ventricular myocardium, causing the ventricles, both the right and the left, to contract simultaneously. At this point, I need to take a little bit of a shift. Previously, we've been talking about the myocytes and those fibers, okay, the cardiac conduction fibers, and I need to actually make a shift into contractile fibers. Contractile fibers are different, okay? So let's just make that move. I want you to think about contractile fibers, not the ones that are necessarily doing the conduction of those initial action potentials that originated in the SA node, but all of the muscle fibers that are going to contract. Remember, the myocytes, those specialized depolarizing cells, were only about 1%, and the rest of the fibers are considered contractile fibers. An interesting thing about the heart is that, or the myocardium, is that there's no myocardial tetanus. You need to remember what tetany is, why tetanus occurs, or how tetanus occurs. But the big thing that's important here is that we don't see tetanus in the myocardial fibers, and that's a really, really good thing. It has to do with the refractory period and how it's placed. We'll look in the next slide at just that. But remember, ventricular contractile fibers are going to do a rapid depolarization. They're going to plateau, and then they're going to repolarize. So let's take a look at that. All right, so this is what an action potential for a contractile fiber will look like. We'll have a rapid depolarization, and you can tell this is rapid by how steep this line is. This isn't a gradual, gentle slope. This is a very steep, rapid depolarization. It occurs because there's a very rapid influx of sodium. So when the voltage-gated fast sodium channels open, the sodium floods in, and that depolarizes the membrane. Remember, sodium ions have a positive charge, so we're going to move from about a negative 90 millivolts on the membrane potential very rapidly up into about the plus 20 range. Next thing that will happen is we'll plateau. And a plateau in this case, what we're referring to is a maintained depolarization. So we've depolarized, and now we're gonna plateau. We're gonna hang on to that depolarization. This happens not because of continued flow of sodium in, but because we have calcium inflow through some voltage-gated slow calcium channels. So the rapid sodium influx pushes us up to depolarization, and then this slower inflow of calcium fibers through channels will will happen, and that'll help to maintain or plateau the action potential. At the same time, calcium is outflowing, so we're losing potassium. We're losing potassium out of that cell through some potassium channels that have opened. So depolarization is all in green, and then what happens is we have a repolarization. Repolarization happens when the calcium channels close, and we stop that influx of calcium. The potassium outflow channels also close, so we stop having that loss of potassium from the cells, and then an additional voltage gate channel opens, and we see potassium actually move into the cell. So not only do we stop losing potassium out, but we gain potassium back into the cell. Just remember, we have switched gears here. We are not talking about autorhythmic fibers. We are talking about contractile fibers. These fibers are different in that they have a stable resting membrane potential right down there, about negative 90 millivolts. When we bring them up to threshold, we form an action potential. Those voltage-gated fast sodium channels open. Sodium floods into the cytosol. It creates a change in the environment. We lose that negative charge, and we produce a rapid depolarization. The channel will automatically inactivate with just in a few milliseconds, and that's why we need the plateau, because once those sodium channels become inactive, we need to maintain that positive ion flow. That's what we see at plateau, or maintained depolarization. It happens for two reasons, partly because we see the opening again of those slow gated calcium channels in the sarcolemma. Open channels mean that calcium moves from the interstitial fluid into the cytosol, which causes even more calcium to pour out of the sarcoplasmic reticulum into the cytosol. So we see really an increase in calcium that's ultimately going to trigger that fiber to contract. But at the same time, we're seeing voltage-gated potassium channels in the sarcolemma open, and that potassium leaves the contractile fiber and aids in sustaining that depolarization. In the red, we have repolarization. Again, this is where we're going to see recovery back down to that resting negative, or that resting membrane potential, or that negative 90 millivolts. And then we have a prolonged delay. So after that delay, we get additional voltage-gated channels opening. We have an outflow of potassium that restores that negative resting membrane potential. We have calcium channels in the sarcolemma and the sarcoplasmic reticulum that are closing. So that's really what's happening here. There's no myocardial tetanus, and I've asked why on the last two slides. And it's because, if you'll notice the yellow on this graph, you'll notice that the refractory period of a cardiac muscle fiber is longer than the contraction itself. So the purple here is the contraction, and the refractory period is actually longer. And that, because of that, tetanus isn't possible. So what that means is a second contraction cannot begin until the previous contraction is well into the relaxation phase. And you will probably remember that tetany happens when contractions happen close together in time, and we get a summation of contraction, and till those fibers have contracted so far that and so rapidly that they can't relax. Remember that a refractory period is a time interval during which a second contraction cannot be triggered. If it could, the heart would undergo tetanus. All of those muscles, those fibers would contract simultaneously, and essentially the heart would stop entirely. So very key, no myocardial tetanus. Also key is understanding this graph and what's happening on the channels. When is the sodium channels open and they're flowing in, and what does that mean to the resting membrane potential? What is depolarization? What is repolarization? And what is the significance of the refractory period being greater than the contraction period? We're going to pick this back up on our next video, and there we go.